Hey everyone, Morgan here. So we're on page 8 of the lecture outline for Equilibrium for Honors Chem. And today we're going to be talking about something that is generally called the ice box. And that is an abbreviation that we're going to get into. It had a different name when I was in school, different names now even, but most people refer to it as an ice box. It's the steps we need to solve an equilibrium problem that is away from equilibrium. Everything we've done up until this point centers around systems that have already achieved equilibrium. And what if we're not at equilibrium yet? So I'm going to write down the steps and then we'll illustrate them. The first thing we're going to do is write the chemical equation. Most of the time that's given, you don't need to worry about it. Second, we're going to write the equilibrium constant. Third, we're going to make an ice box. Fourth, we'll fill it in. Fifth, we'll plug into KEQ. Sixth, we're going to solve for X. And then finally, we're going to answer the question. All right. So, this might look familiar to you, the quadratic form. We know if we're in the quadratic form, we can solve for x by saying x equals negative b plus or minus b squared minus 4ac, that's all under the square root sign, all divided by 2a. That is often called the quadratic formula. Okay? So, I have this reaction. It's an equilibrium where A turns into B plus C. So I'm going to say A turns into B plus C. I know that KEQ is going to equal the concentration of B times the concentration of C over the concentration of A, and I'm assuming that's already balanced. An ice box has the letters I, C, E, and they stand for initial, change, and equilibrium. Once again, that's initial, change, and equilibrium. And in this question, I'm starting off with 0.10 molar A, and I want to find out what the concentration of B is at equilibrium. Okay. Initially, I don't have any B and C because A hasn't reacted yet. When A reacts, the amounts change. C for change. A goes down by some unknown amount that I'm going to call X. And B and C both go up by an equivalent amount. It's a 1-to-1 mole ratio there. So for every X that falls off here, I get 1X there. Then at equilibrium, I add these two lines together, 0.10 minus X, X and X. All right. So now, let's do some math. Let's plug in here. I know that that equals 3.0 times 10 to the negative 6. That's a given. That's a very small number, which means I don't have very much B or C. The amount of B I have is X times the amount of C, which is X, divided by 0.10 minus X, and that equals 3.0 times 10 to the negative 6th. Okay. X squared over 0.10 minus X equals 3.0 times 10 to the negative 6th, or x squared equals 3.0 times 10 to the negative 6th multiplied by 0.10 minus x. And when I distribute that, x squared equals 3.0 times 10 to the negative 7th minus 3.0 times 10 to the negative 6th x. And with just a little bit of arithmetic, I can put this into the quadratic form. X squared plus 3.0 times 10 to the negative 6th minus 3.0 times 10 to the negative 7th equals 0. Now, I could solve that using the quadratic equation. Or I can go a little old school. See, it turns out that since the KEQ is so small, I can basically assume that this minus x, when you round off for sig figs, will still equal just 0.10. So let's do it as an approximation. X squared over 0.10 is approximately equal to 3.0 times 10 to the negative 6th, or x squared is equal to 3.0 times 10 to the negative 6th multiplied by 0.10, and I can take the square root of the whole thing, and x equals 5.5 times 10 to the negative 4th. Okay? Now, let's look at something. What if I actually wanted to do this, okay, as a quadratic equation? So, on my calculator here, I have a quadratic solver, okay? Choose that. A in this case equaled 1. B equaled 3.0, second EE, negative 6th. And C is negative 3.0, second EE, negative 7th. You see that comes from these right here. Now when I hit enter, I can ignore the negative root. Negative roots are no meaning in chemistry. I'm getting 5.46 times 10 to the negative 4th. Now if I round that off to 2 sig figs, that's 5.5 times 10 to the negative 4th, which is exactly what I got by doing the approximation. So it's a really valid approximation, and I don't have to go through all this work. I know many students that do all this work just because they're good at it and their calculator can help with it. Okay, so I've solved for x. Now I need to answer the question. Let x equal the concentration of B, which equals 5.5 times 10 to the negative 4th molar. And I know that that is accurate because x is what represents B. Now, often I will do what is called a percent ionization test here to make sure that x is less than 5% of the original value, the 0.10, which means it's going to round off to be the same thing. So I'll take that answer, 5.5 times 10 to the negative 4th. I'll divide by 0.10. I'll multiply by 100%. Well, I can use a calculator to show you what that is, but just looking at it, I can tell you it's very tiny. 5.5 second EE negative 4th divided by 0.1 times 100%, and I'm getting 0.55%. And as long as that is less than 5%, 0.10 minus x still rounds off to be 0.10, and my assumption is very valid. Okay, and that's how we set up an icebox problem. We're going to give you folks a lot of practice with that. Thanks for tuning in. This is Morgan signing off.